Good morning dear students, welcome back. So this is the continuation of my sample question paper discussion. I have already uploaded 2 videos on selected questions for electronics and electrical engineering stream branch, applied physics for electrical, electronics and allied branches. So here is the question from module 3. Module 3 is about lasers and optical fibers. Question number 5 goes like this: define laser and discuss the interaction of radiation with matter. See, this question they can also ask like this: obtain the expression for energy density using Einstein's theory of A and B coefficient. If that is the case, answer will be having derivation part, that is BE-2022 is equal to BE-21 you have to derive, and that will be for 10 marks. Here he is asking only interaction, 3 interactions you have to explain, and definition for laser 1 mark, 3 interactions 2 marks. So it goes like this: laser is a short form of light amplification by stimulated emission of radiation. Dear students, laser is a short form: L for light, A for amplification, S for stimulated, E for emission of, R for radiation. And when light falls on the substance, the matter will interact with radiation or electromagnetic wave in 3 different ways. First one, interaction is like this, and before that you have to explain little bit about the matter. In the matter, atoms will be in the different energy levels. Lowest energy level is ground state, I call it as E1, and all other higher levels are excited states. So you can take any one of them. Let us take E2 as one of the excited state. So E2 is greater than E1, and normally under normal temperature atoms will be in the ground state. More atoms you find in the ground state, few atoms you will find in the excited state. So atoms in the ground state I take it as N1, atoms in the excited state I take it as N2. So N1 is always greater than N2. Now when light of certain frequency incident on this system, 3 things will happen. Number 1, induced absorption. Radiation can be absorbed by the atoms which are in the ground level. As a result, atoms will go to higher level from E1 to E2. This is known as induced absorption. And next one, after they go to higher level, they stay over there for a short period of time, about 10⁻⁸ seconds, and then they will come down without anybody's support. That is called spontaneous emission. So after spending 10⁻⁸ to 10⁻⁹ seconds, atoms come down to the ground state by emitting the excess energy in the form of radiation. So this is happening without anybody's support. Spontaneous agagodrinda, we call it as spontaneous emission. Next one is stimulated emission. This is the speciality of Einstein's theory. Einstein introduced a new type of emission called stimulated emission. What is the stimulated emission? See, atoms are already in the excited state. They were about to come down to the ground state. Before they come, you send the radiation. Then this radiation will instigate the atom, influence the atom, induce the atom, and will send one message to the atom. What message? You can go to the ground state now. That type of message it will send. By sending that message, by influencing the atom to come down to the ground level, the incident photon will not lose any energy. It will come out without any problem. Same frequency will come out. In addition to that, because of the de-excitation, you get one more photon. So that way you get 2 photons coming out. That is the speciality of stimulated emission, and it is essential for getting the lasing action. After all, what is laser? Laser is a process in which more and more identical photons are emitted in the same direction. Spontaneous emission, photons are emitted but not identical, but not in the same direction. Whereas in laser, because of this type of external stimulation, identical photons in the same direction are emitted. So that is what this sentence says. If the atom is already in the excited level, that is very important. Atom must be in the excited state. Then the incident photon may influence the atom to undergo the transition. This type of influenced transition is known as stimulated emission. So these are the diagrams. First diagram, photon is incident, this wave structure is photon is incident, atom goes to higher level, induced absorption. After brief interval of time, it will come down emitting the photon. This is a spontaneous emission. Here, induced photon, sorry, incident photon, atoms are in the excited state. It is not only influencing one atom, it is influencing all the atoms. As a result, all of them will come down emitting more number of photons. So in order to achieve lasing action, it is better to have more and more atoms in the excited state. That means N2 should be greater than N1. That N2 greater than N1 is known as population inversion. So this is about interaction of radiation with matter. Now Next question is on optical fiber. Define angle of acceptance or acceptance angle and numerical aperture, and hence derive the expression for numerical aperture in terms of refractive index of core, clad and surrounding. Dear students, you know optical fiber is a device which consists of optically dense medium, that is called core, and little bit thin medium, that is clad and surrounding. And inside the core medium, if you send the electromagnetic signal, it undergo total internal reflection and keeps on propagating. For this total internal reflection to happen, you have to send the ray in a particular direction, you have to send the ray at a particular angle, and that angle is known as angle of acceptance. So here comes the definition. Angle of acceptance or acceptance angle, it is also called as contact angle, is defined as the maximum angle of incidence of the light beam at the center of the fiber. See, if this is the fiber, at the center you are sending the light here, and once it gets in there, it continues to travel in the zigzag path. So at the center of the core, up to which total internal reflection takes place at the core clad send interface. Suppose if you send the ray beyond that, then the ray will not undergo total internal reflection. Critical angle condition is not satisfied. So this is the definition of angle of acceptance. It is a maximum angle at which the ray enters into the fiber and continues to travel within the fiber. This maximum angle of incidence is known as acceptance angle. Well, next is numerical aperture. Numerical aperture, actually it is defined like this. It is the product of refractive index of the surrounding medium. Suppose if I take this as the optical fiber, surrounding medium, and then sine of theta naught, where theta naught is the angle of acceptance. But it so happens that surrounding is air, so we take it as 1. N naught is equal to 1 because air refractive index is 1. So by and large we define numerical aperture as a sine of angle of acceptance. But strictly speaking, it is not sine of theta naught, it is N naught into sine of theta naught. Look at the statement. It is a product of refractive index of the surrounding medium and sine of the acceptance angle. So this is definition. Alge first part answer is over. 2 marks ready now. Now we will go ahead with the expression for the numerical aperture. Dear students, first you have to draw the diagram. I just explained the diagram. Look at this shaded region. This is the clad region, and inside this is the core region. So this portion is core and surrounded by clad and surrounded by what is called skin or outer protecting layer. And this dotted line is axis of the optical fiber, also called as core axis. Core refractive index is N1. It is very much greater than, not very much greater than, compared to N2 it is greater. Core and clad is N2, core is N1, N1 is greater than N2. And the ray of light is incident at O. Look at this is theta naught. Suppose if this angle is more, means if the ray is coming like this, then it is not accepted. Beyond that it is not accepted. Below that it is accepted. So when a ray enters, no, it bends towards the normal because it is traveling from rarer to denser, O to B. At B it is grazing the surface, provided this angle is equal to critical angle. So this angle is critical angle. If this is critical angle, then this angle of refraction is 90 degree, it will graze the surface. Suppose if this is greater than critical angle, then this ray will bend back into the optical fiber and continues to propagate in this zigzag medium. Now we have to apply Snell's law at 2 positions, that is at position O and position B, at a point O and point B. Please look at this diagram because the diagram carries more weightage. Now explain this diagram in your own words. What to write I have given here, just you read the paragraph and you can put it in your own words. Like N0 equals refractive index of the surrounding, N1 equals refractive index of core, N2 equals refractive index of clad, AO equals incident ray, OB equals the refracted ray, BC is equal to ray grazing the surface. OB, if you want you can call this as BB dash, B dash, so that OB dash is critical angle. Ee tara diagram ana explain maadi. After that you can proceed with the application of Snell's law. I repeated the diagram once again. Now I am applying the Snell's law at O. First I apply the Snell's law at O. You know what is Snell's law? N into sine theta. That means refractive index of this medium into sine of the incident angle. Refractive index of this medium is N naught into sine theta naught is equal to next refractive index of this medium into angle of refraction. refraction, that is n naught sin theta naught equals n1 sin theta 1. This is from PUC only. n1 sin theta or n1 sin I is equal to n2 sin r anta barita idralla adena ide. Then after rearranging, you get sin theta naught equals n1 by n naught into sin theta 1. Now I just want to replace this sin theta 1 because my final intention is to get the sin theta naught, because sin theta naught, as you all know, is nothing but numerical aperture. Okay, let us apply the Snell's law once again. Now this time it is at B. Illi apply madadaga, this medium refractive index is n1, that is n1, and incident angle is this one, that is critical angle. It is nothing but 90 minus theta, because this total angle is 90, and if this is theta 1, this is the corresponding angle, this is theta 1. Just look at the diagram, you can make out how this becomes 90 minus theta. So 90 minus theta 1 is equal to n2, that is this medium, n2 into sin 90, that is angle of refraction. Well, after little bit of calculation, we get this equation. Sin of 90 minus theta is cos theta, sin 90 is 1, so I have n1 cos theta 1 equals n2. Next, cos theta 1 is equal to n2 by n1. Remember, I want to replace this sin theta. For that, I take the help of cos theta. You know the relation between sin theta and cos theta. Sin theta is equal to root of 1 minus cos square theta. That trigonometric identity I am using. Well, so sin theta na nanu illi tagitini, from the equation 1 I remove. Then sin theta naught is equal to n1 by n naught into root of the sin theta 1 becomes 1 minus cos square theta 1. Now it is very simple, because I have cos theta already here. Substitute n2 by n1 whole square in place of cos square theta. That is what I am doing here. So sin theta naught is equal to n1 by n naught into root of so much. Now you do small simplification, take n1 LCM, right, and then cancel n1 and n1 square. See, in this n1 square is LCM, n1 square LCM, numerator becomes n1 square minus n2 square, n1 cancel, and take n naught this side, n naught sin theta naught is equal to root of n1 square minus n2 square. And you know n naught sin theta naught is equal to numerical aperture, so numerical aperture is equal to root of n1 square minus n2 square. Dear students, I tell you, this is also one of the important derivation and most expected question also. Well, that's all about the question on optical fiber. With this, I move on to numerical problem. This problem is on lasers. See, in lasers, while deriving that Einstein's theory A is equal to B, or B1 equals so B12 equals B21 theory martirala, there you come across with one parameter called Boltzmann factor. Boltzmann factor is n1 by n2 is equal to e to the power of hc by lambda kt. That formula we are using to solve this problem. Enidu problem? The ratio of population of two energy levels is 1.059 into 10 power minus 30. What is the wavelength of the emitted laser at 330 Kelvin? So temperature given, population given. One thing you must observe, see, if this 10 power is minus 30, please take it as n2 by n1. If 10 power is plus 30, you take it as n1 by n2. So many students, they do this mistake. Yakendre alli avaru sumne population of two energy levels anta heltare, which to which anta helalla. It is understood, higher to lower andre population kadme irbeku, because n2 is less than n1. Lower to higher adre population jaasti irbeku, that is 10 power 30. Okay, so illi 10 power minus 30 kottirodrinda, it must be n2 divided by n1. Okay, the problem goes like this. Nodi nanu heldange, n2 by n1 is equal to 1.059 into 10 power minus 30. T is equal to 330 Kelvin. This is the Boltzmann formula. I said no, n1 by n2 is Boltzmann factor. n1 by n2 yen agutte, I just write n1 by n2. Okay, n1 by n2, this is nothing but Boltzmann's factor, e to the power of hc by lambda kt, but I want n2 divided by n1, so just I take the reciprocal means minus hc by lambda kt. So therefore this equation is here. Now simplify. By simplifying, keep on simplifying, just watch the steps, you will get an idea. What I have done here, hc by lambda kt is equal to ln. Just to remove exponential, I take natural log, that is ln. Next I want lambda, because in the question you need to calculate wavelength. Lambda you send this side, remaining send this side, it becomes minus. Small simple algebraic operations sustain. You have done this cross multiplication and other things n number of times already. Well, after that substitute the values, simplify. Pause this video and then do the calculation. In your calculator, remember, you have to press ln button for finding this ln value, not log button. LOG is for log to the base 10. LN is natural log. Okay, so you must know how to operate the calculator. In calculator there is LN button that you have to press, and the answer is 632 nanometer. Okay dear students, I move on to the next question. This is also another important question. Construction and working of carbon dioxide laser. Explicate different vibrational levels in carbon dioxide and hence give the construction and working of carbon dioxide laser. ನೋಡಿ ಇಲ್ಲಿ ಕಾರ್ಬನ್ ಡೈಆಕ್ಸೈಡ್ ಅಲ್ಲಿ ಏನಾಗುತ್ತೆ, ಇಟ್ ಈಸ್ ಒನ್ ಆಫ್ ದಿ ಪವರ್ಫುಲ್ ಲೇಸರ್, ಹೈ ಪವರ್ ಲೇಸರ್, ಅಂಡ್ ಇನ್ ಫ್ಯಾಕ್ಟ್ ಇಟ್ ವಾಸ್ ಡಿಸೈನ್ಡ್ ಬೈ ಇಂಡಿಯನ್ ಆರಿಜಿನ್ ಫಿಸಿಸಿಸ್ಟ್ ಬೈ ನೇಮ್ C.K. Patel. Okay, in 1960s. Even today it is used for high power applications. Carbon dioxide laser is a very highly powerful laser beam. Using carbon dioxide you can even cut metals also. Okay, whatever it may be. How actually it works, what is the background? In carbon dioxide molecule we have two oxygen, at the center one carbon, CO2. Okay, these molecules they vibrate like this, they vibrate like this, they vibrate like this also. Okay, so depending on how they are vibrating we classify them into three groups, namely symmetric vibration, asymmetric vibration, bending vibration. They are like this. First, symmetric vibration. What is the symmetric vibration? Read it. Carbon atoms are at rest, both oxygen atoms are vibrating. Carbon ಮಧ್ಯದ್ದು centrally fix ಆಗಿರುತ್ತೆ, ಬರೀ oxygens ಮಾತ್ರ vibrate ಆಗ್ತಾ ಇರುತ್ತೆ to and fro. This is nothing but symmetric vibration. They come towards each other, go away, come towards, go away. This is what is called symmetric vibration, and these vibrations are represented by 100. Next, asymmetric. Oxygen are going like this, carbon is going like this. So carbon and oxygen are vibrating in the opposite direction. Okay, when carbon is coming this way, oxygen is going like this. So this is asymmetric vibration. Okay, and it is represented by 001. Next, bending. Right, see this entire thing, for example this is oxygen, this is oxygen, at center I have carbon. When carbon comes down, oxygen goes up, oxygen goes up. When carbon goes up, oxygen will come down. Okay, oxygen ಕೆಳಗಡೆ ಬಂದಾಗ carbon ಮೇಲೆ ಹೋಗುತ್ತೆ, when carbon comes down oxygen will go up. This is nothing but bending vibration. Look at the diagram here. Brown color circle carbon, that pink color circles are oxygens. See, look at the first diagram. Here both oxygen are moving towards each other but carbon is simply at rest, therefore this is symmetric. And here oxygen is going like this, carbon is going like this, they are going totally opposite. This is asymmetric. Next, when oxygen and oxygen going up, carbon is coming down, this is bending. Artha aitalva? So this is about carbon dioxide vibrational modes. Sometimes they ask this itself for 5 marks ಅಥವಾ 6 marks ಆ ಥರ ಕೇಳ್ತಾರೆ ಆಯ್ತಾ. ಇಲ್ಲಿ ನಾನು ಕೊಟ್ಟಿದ್ದೀನಿ. ಸೊ ಇಲ್ಲಿ ಕಾರ್ಬನ್ ಡೈಆಕ್ಸೈಡ್ ವೈಬ್ರೇಷನಲ್ ಮೋಡ್ಸ್ ಅನ್ನು ಮೆನ್ಷನ್ ಮಾಡಿ, ಅಂಡ್ ದೇರ್ ನೋಟೇಷನ್ಸ್ 001, 010, 100 like that. All these details are available here. Now coming to construction, look at the paragraph. In carbon dioxide laser we have a glass tube or quartz tube about 10 cm long, and inside this tube we have three gases, namely carbon dioxide, helium and nitrogen, and they are filled in the ratio 1:2:3, means 1 part of carbon dioxide, 2 parts of helium, 3 parts of nitrogen, and they are filled at a pressure of 6 to 17 bar. High pressure alli fill up ಮಾಡಿರ್ತಾರೆ, and then some part of water, little bit of hydrogen is also included and water vapor also added to the tube for the purpose of oxidizing carbon monoxide to carbon dioxide. Carbon dioxide ಸ್ವಲ್ಪ ಕಡಿಮೆ percentage ಇರುತ್ತೆ. Sometimes inside the tube carbon monoxide is generated. To convert carbon monoxide to carbon dioxide we put some water vapor or hydrogen into the tube. Okay, and this entire tube is connected to both AC and DC power supply, and at the end of the tube we have what is called mirrors, called Brewster windows, in order to provide maximum polarization, because we want to have highly polarized laser beam. Highly polarized laser beam is more powerful laser beam. So both the ends are fitted with what is called quartz glasses or quartz polished surfaces called Brewster's windows. So that much is given in this paragraph. Okay, now the diagram goes like this. Look at the diagram. The tube is filled with carbon dioxide, nitrogen and helium inside, and I have DC power supply, right? And then I have mirrors, completely silvered mirror, partially silvered mirror. These yellow lines represent quartz. They are called Brewster's windows. Okay, now when you switch on the DC source, the electrodes will give a spark, and inside this tube, there will be a sort of discharge, and the electrons release agtave. Electrons release agbittu, those electrons will go and hit nitrogen. First they will hit nitrogen. Look at the energy level diagram. See, this is energy level diagram. First part represents nitrogen level diagram. Second part represents carbon dioxide level diagram. Now I will explain. So highly energetic electron will come and hit nitrogen atoms. First nitrogen atoms ana dikki hoditave. Then all nitrogen atoms will go to N2 level. L2 level. N2 is the nitrogen. L2 is the excited state in the nitrogen. So all the nitrogen atoms will go to excited state. And remember, in nitrogen we have metastable state, and existence of metastable state is compulsory for lasing action. Then only you can achieve population inversion. Okay, so all the atoms will go to L2 level in the nitrogen. Once atoms get accumulated in the N2 level, okay, they will transfer energy to carbon dioxide. Now all the carbon atoms will go to that particular level which I labeled as E5. Don't worry much about what is this L2, L1, E2, E1, E3. Simply they are representing energy levels. Actually there is a perfect meaning for each and every level, but it is not required at this level. Okay, at this stage it is not necessary. Sumne neevu avuna ground level, excited level, metastable level ee tara treat ಮಾಡಿ ಅಷ್ಟೇನೆ. So when electron, fast moving electron hits nitrogen, nitrogen goes to excited state. Here it is metastable, therefore population keeps on increasing. Once the population reaches maximum, the entire nitrogen gas molecules will transfer energy to carbon. Nodi electron bandu dikki hoditala illi, this is called first collision. In the first collision or the first kind collision, nitrogen is excited. Now there is another collision. Nitrogen is colliding with carbon dioxide. Idu eradane dikki idu. This is called second kind collision. Nitrogen ella mele hogi accumulate admele carbon dioxide jothe dikki hoditave, interact ಮಾಡ್ತವೆ, they collide each other. This is called second collision, second kind collision. In second kind collision, what happens? Entire set of carbon dioxide molecules which were there in E1 level, all of a sudden they will go to C2 level, E5 level. Ella onde sarti ಮೇಲೆ ಓಡ್ ಬಂದ್ಬಿಡ್ತವೆ. Okay, now the population rises to the maximum extent here immediately. Illi nitrogen nalli gradually population increased, but in carbon dioxide all of a sudden it increases. Okay, now once the population reaches maximum value, transition starts. From here to here there will be stimulated emission. From here to here there is stimulated emission. That is from E5 to E3, E5 to E4 there will be stimulated emission. Only these two are stimulated emission. Don't ask me why there are no other stimulated emissions. It is not that simple, that easy to explain. We have to know the meaning of quantization, conservation, angular momentum number. Okay, there are many things involved here. Okay, conservation of angular momentum, conservation of orbital quantum number, ಈ ತರ ಏನೇನೋ ಬರುತ್ತೆ. ಅದರಲ್ಲಿ ಈ ಲೆವೆಲಿಗೆ ಬೇಡ, ಇಷ್ಟು ಮಾತ್ರ ನೆನಪಿಟ್ಕೊಳ್ಳಿ. Only try to remember only this much. What? Once population in carbon dioxide level increases maximum, then transition starts. Stimulated emission, stimulated emission. These two stimulated emissions will give two different laser beams. Afterwards, carbon dioxide molecules will slowly come here and settle down here. Meanwhile, nitrogen atoms are already kicked to the next level. Again they will hit carbon dioxide. Again they go, and this story continues. Andre, as long as the source is on, electrons are released. Those electrons will collide with nitrogen. Nitrogen will go to L2 level. Nitrogen collides with carbon dioxide. That is called second kind collision. Carbon dioxide will go to E5 level. From E5 to E4, from E5 to E3, stimulated emission takes place, laser is obtained. All these things are explained in this paragraph. Just pause the video, read it. I said there are two lasing actions. One is E5 to E4, that is this red color, E5 to E4. It gives a wavelength of 10.6 micrometer, and E5 to E3 gives 9.6 micrometer. Dear students, I tell you one thing. Some students are asking, sir, how to score maximum marks, more marks? See, these small things actually makes a lot of difference. If yaro opa lasing action ella explain madtane, he will not write the wavelength of the laser emitted. For that 1 mark is reserved. If you don't write the wavelength, you lose 1 mark. So you don't give any chance. Don't take any chance. Don't leave any stone unturned in the process of getting full marks. So you write the wavelength also. If you forget to mention the wavelength, 1 mark they will deduct. Energy level diagram, if you don't mention properly, 1 mark you will lose. Okay, so you must know where I am losing marks, not where I am getting marks. If I don't write the wavelength, I lose marks at the gottidre, then you will write the wavelength. So this is about the construction and working of carbon dioxide laser. Now coming to the next question, discuss the types of optical fibers based on the modes of propagation and refractive index profile. Actually, there are 3 types of optical fibers, namely single mode, and then step index multi-mode, and then graded index multi-mode. First I will take up single mode. See, in this what is most important is the dimensions of the core. See, the single mode consists of very thin core material. Bracketally you have to mention the value. Again, this is the way the difference lies between average and above average student. Average students ಏನು ಮಾಡ್ಬಿಡ್ತಾರೆ, thin core material ಅಂತ ಬರೀತಾರೆ. ಅದೇ above average, those who want to score maximum marks, they mention the value also. 8 to 10 micrometer you have to mention, that is the core size. And then cladding, this cladding is thick. Core is thin, cladding is thick, diameter is 60 to 70, ಅಂದರೆ 10 times ಜಾಸ್ತಿ ಇರುತ್ತೆ. ಇದು 80 ಇದ್ರೆ ನಿಯರ್ಲಿ ಇದು 70 to 80 ಇರುತ್ತೆ. And uniform, in both the cases the refractive index is uniform and the refractive index profile is a step. So sharp ಆಗಿ ವೇರಿ ಆಗುತ್ತೆ. Look at this diagram. So this is core region. Look at the circle, very small circle, about 8 to 10 micrometer. Look at the next circle, this is clad region. It is 60 to 70, you can even go up to 100 also. Next, core region refractive index is very small but constant. Very small in the sense the value is high only. The region is very small. Refractive index, higher refractive index but over a small distance. Look at this one. Okay, and suddenly decreases. Afterwards, this is region is more, the value is less. I hope you are getting. Refractive index of clad is less, let us say 1.45, whereas core it is 1.55. 1.55 is more, but over how much area? Over a small area. How much distance? Over a small distance. Because the core is so small, it cannot support too many signals to propagate. Therefore, it is called single mode. Onde ಒಂದು ray ಅನ್ನು ಕಳಿಸಲಿಕ್ಕೆ ಸಾಧ್ಯ. Suppose if you increase the dimension, you enlarge the core size, enlarge the clad size without changing the refractive index, then it becomes multi-mode. Step index only. Why it is called step index? Because refractive index is varying in the form of step. Metal ತರ ಕಾಣಿಸುತ್ತೆ ನೋಡಿ ಅದು refractive index. Refractive index is, it is like this and then like this and then like this. This is the reason why it is called as a step index. Okay, so now you look at the size of the core and clad in this particular case. Core is 50 to 200, clad is 100 to 250. Refractive index profile is very much similar to single mode fiber only. Okay, refractive index profile alli changes irodilla, and the shape alli change irodilla. Nodi shape ade tara ide, even here also it is step only, but this portion was earlier very narrow, now it is widened. Look at the center, core was very small circle earlier, now it is a big circle because the dimension has been enhanced. Because it is too big in size, I can send many optical signals into the fiber. Okay, now this is about the multi-mode step index. Now retain the same dimensions, core that much big only, clad that much big only. Instead of having constant refractive index, you have gradient refractive index, gradually decreasing refractive index. That means this refractive index, instead of retaining 1.55 always, you keep on reducing 1.55, 1.54, 1.53, 1.455, sorry 5, 1.45 like that. So gradually if you decrease, then it is called graded refractive index or graded index multimode fiber, short form GRIN. Look at the dimension, still it is 50 to 200, 50 to 200. External diameter, still it is 100 to 250, 100 to 250. But the question is, the difference is, refractive index of the core is not uniform. I am not bothered about clad. Clad is constant only. No, clad is uniform, whereas core is not uniform. Okay, core is not uniform. The refractive index of the core is not uniform. See, I am not just reading the answer. I am not just reading the answer, I am explaining the concept. So you try to understand, you can make your own sentence. Like in graded index multimode, core is big, about 100 to 200, clad is also big, about 100 to 250, but the difference is refractive index is not constant, it is gradually decreasing. So see the profile, earlier it was in the form of step, now it is in the form of a hump, that gradually decreasing, afterwards it becomes constant. So this is about types of optical fibers. Now comes numerical on optical fiber. Question number 6C. Find the attenuation in an optical fiber of length 600 meter. Remember, in this type of problem, attenuation problem, you have to take length in kilometer. 600 meter kuttidru kuda, you convert that into kilometer. Only in this particular segment, you have to convert that into kilometer. 600 meter is equivalent to 0.6 kilometer. Light of power 120 milliwatt emerges with a power of 85 milliwatt. Input power given, output power given, you have to find out alpha. Alpha is the attenuation coefficient, and the formula is here, minus 10 by L log of P out by P in. Okay, I told you, L should be in 0.6, that means L should be in kilometer. Now by taking L in kilometer, I will substitute the values, just I will do it for you. Alpha is equal to minus 10 by 0.6 into log of output power is 85 divided by input power is 120. Both are milliwatt, so milli cancel. So simplify. If you simplify, I do it, 85 divided by 120. For that log, now this time it is only natural, log to the base 10, no ln. Okay, into 10, right? Just 1 minute. 85 divided by 120. For this I take log, right, into 10, that divided by 0.6, it comes up with 2.49. So alpha is 2.49 and the SI unit is decibel per kilometer. So this is the answer for this particular question. Okay, dear students, I will stop this video here. As usual, I will come back with remaining questions immediately. So you need not have to wait for a long, because I know your attention. I know there is a very short period of time. Your exams are fast approaching. So keeping that in mind, I would like to upload as many videos as possible within 1 or 2 days. Okay, please stay with me and also give your positive comments. Thank you. Thank you very much.